All right, so structure of matter is where we are. We're going to talk about the atom today, atomic arrangement, atomic numbers, how the atoms are, how we think we understand what an atom is. So just for historical context, we're going to talk about the different models, and you can kind of flip over to page 36, and you can see the different, models that we've looked at over eons, really. So we're going to go all the way back to the Greek, and really the main thing that you need to know about the Greek is that they kind of came up with the word. They didn't have the high-powered microscopes that we have now, but they were smart enough to realize that if you took something and you cut it down to its smallest possible form, then to cut it down any further, it would become something totally different. Like I got a glass of water up here, a cup of water up here, and what is water? H2O, right. So what does H2O mean, though? Two hydrogen, one oxygen atom, right, creates water. Okay, so water is not an element, right? It's a compound, really. We'll talk about that here in a bit, but it's a compound. The elements are the individual pieces to it, the H2O. But let's assume and make believe water is an element. All right, so if you were to take in, if I were to empty this cup, half empty this cup into another cup, what would I still have? Water. I'd have 2 cups of water, right? And I could continue to do that over and over again until I've got maybe even 1 drop of water in individual containers, and what would I still have? Water, right. If I continued to do that until the point where the H and the O separated, would I have water anymore? No. And so it is with the atomic structure. You start off with, just a group of atoms of any kind, and you continue to cut them down, and eventually you're going to get to a point where if you cut it any further, you might have a nuclear explosion, but you're also going to have a different atom, right? So they came up with a word to describe what the smallest possible portion of something is before it becomes something else, and that's what they call an atom. An atom just means uncut, indivisible, anything below that, and it becomes a different element altogether. So that's what the Greeks envisioned, and they, again, didn't have microscopes like what we've got now. So their idea was that they had 4 substances that existed in 4 different essences. So is that really important to remember? And the answer is not really. You can memorize that. Certainly you need to know the definition of the word atom, and that would be uncut, indivisible, the smallest portion of something. So the development of the atomic model, if you look again on page 36, the figure 3.2 is kind of representative of the Greek idea. And if you look at the medieval idea of what an atom is, then it's really not unlike the Greek model very much, right? You got 4 different things, and they kind of exist in different levels. And so we clicked along with that model for probably 3,000-4,000 years, right? A long time until we got closer to the 20th century, 19th, 18th century. And they started discovering different elements, individual elements, and they also started discovering that the things like water were not, an element of themselves, but rather a combination of elements. So this guy Dalton comes along and he says, well, individual elements can combine to create something that behaves totally different than either one of the other elements. So going back to water, what is hydrogen? It's an element, but it's a gas, right? What is oxygen? Also a gas. What is water? It's a liquid, right? So, you combine some stuff together and it can behave in a totally different way than the 2 individual particles all by themselves. So Dalton said, okay, well, we have to have a way to combine those things. And he envisioned atoms as having a means of combining themselves. This wasn't literal, but this was kind of a figurative thing, kind of like if you've ever been in a house that had a screen door. And I'm not talking about one with an automatic closer, but it might have a spring or maybe a gate that had a little hook, and then you close the gate and you put the hook through an eye bolt that's screwed into the door frame or into the gate post. That's what he envisioned. You know, some had eye bolts and some had hooks, and you can join them together with hooks and eyes. So that Dalton, you know, his big contribution was a combination of individual molecules to create something that behaved differently, right? So that was his contribution. Didn't really know, you know, subatomic particles. So along comes Thomson, and you know, full disclosure, I've never seen plum pudding in my life, but that's what he envisioned, was that an atom, yeah, they could combine together, but they had individual parts. So what he envisioned was a defined nucleus composed of something, and then you had electrons on the outside of it. So the electrons, you know, looking at the diagram on page 36, looks more like pineapple than plums to me, but all right, the plums on the outside of this plum pudding represented those electrons. And then Niels Bohr came along with a different model, and it's still the model that we use today, atomic theory. You know, you can look into things like string theory that may better explain certain things. But what we're going to discuss in this class is going to be the Niels Bohr atom. All right, so Niels Bohr kind of built on Thomson. He said, okay, we've got a nucleus, and a nucleus is made up of subatomic particles, and we're only going to focus on two that are inside the nucleus. Really kind of three, but for the most part two inside the nucleus, and the electrons are on the outside. So what it looks like then, if you were to kind of simplify his drawing there, is instead of being a plum pudding model, it looks more like a solar system. Okay, so you got a very well-defined nucleus, and then you've got these planets, you know, it's kind of like the sun, and these planets buzzing around the outside of them. Where the description kind of fails is that, you know, in the atomic structure in the Bohr atom, we've got not just the planets, so to speak, but we might have multiple planets in the same rough orbit, okay? So subatomic particles that we've recognized, we've got inside the nucleus, we have two, and that is, for the most part, a proton, which is positively charged. You know, if you're for something, you are pro something, right? So a proton is positively charged, and then you've got the other one, which it doesn't really have a charge. So, you know, the setting in your car, you shift into the N, you're not going forward, you're going backwards, it's neutral. Right, so it's a neutron. So we have proton and neutron on the inside, and what I want you to be thinking of is the neutron is neutral, not by virtue of it having no charge, really. So this is where the car analogy fails, but rather it's neutral because it has offsetting positive and negative charges within it. Okay, so more on that probably next Friday. I don't think we're going to get into that today. But it's neutral because it's got offsetting charges. The positive charge and negative charge cancel each other out, and therefore it's neutral. Okay, so we also then have electrons on the outside. The electrons should, but don't always necessarily have to equal the number of protons. And again, what we've got are offsetting charges. So we've got one positive charge, one negative charge. The entire atom in this case is neutral. Okay, so when we talk about ionization, this is jumping ahead just a little bit, what we're talking about is selective removal of electrons, right? We're not going to remove any protons, sort of, unless we're dealing with radioactive decay, and we'll talk about that again next week. But when we ionize something, it's going to be because we removed an electron. So we talked about this before. I knocked that electron out, and it's floating around out there. Is an ion. It's a negatively charged ion. It's a charged particle, right? Well, this is too. and together we call that an ion
Pair.
pair. Right. So atomic structure. All right. So if we're going to make an equivalence between the atomic structure in the Bohr atom and a solar system, then we're going to look at our solar system and we're going to say, what's the solar system made of primarily? What is in the solar system mainly?
Space.
It's just empty space, right? And distance between here and the sun is a long ways, right? So you talk about, I think light, it takes like 8 minutes for light to get from the sun to the earth, traveling at 186,000 miles per second. Pretty quick, right? Moving fast, and it still takes 8 minutes. I think it's 8 minutes. So what planet are we? There was a TV show. Third rock from the sun, right? We're the third rock from the sun. So being, in all the planets, we're relatively close, and it still takes that much time for it to get to us. So the main thing that we've got is empty space. And the same thing with the atom. In our atomic structure, the atom is very tiny. The atom is very tiny, but most of that tiny space is empty. There's just nothing there. All right, so for an example, for an illustration, if we had a hydrogen atom, and a hydrogen atom, that's what this is, whether or not it's got a neutron is irrelevant, but if it only had one proton, and that proton was the size of a basketball, any idea how close the electron would be?
7 miles.
Well, you're on the right track. A long, long ways compared, to this, what I've drawn up here, is 2 miles. So I got a basketball sitting on the floor in here, and you walk 2 miles away from it. Can you see the basketball? No, you can't. I don't care how good your eyes are. You're not going to see the basketball. I don't care how flat it is. You're not going to see it, right? So a lot of empty space. And how empty is going to be determined by really what your nucleus looks like. So we'll get into that again here in just a bit. I want to make sure I stay relatively on track. So we've got the Greek atom, Greek model, we've got the Dalton atom, the Thomson atom, we're sitting on the Bohr atom now. The Bohr atom has a well-defined nucleus, and it's got electrons screaming around the outside of the nucleus, and the shells we'll define here in a bit. So just some terms that you need to be aware of, and it might help if you flip over to page 38 and look at the table at the bottom. Okay. So at the bottom, what you've got is the particle, subatomic particle. So that's table 3.1. You got the subatomic particle, and we're only going to focus on 3. That's the electron, proton, and neutron. Then you've got the location and where those can be found. The location for the electron are going to be in the shells. We're going to call these shells, even though it's really orbit. All right, just like, again, a solar system would orbit around the sun. The electrons orbit around the nucleus. So they exist in the shells. The location for the proton and the neutron are inside the nucleus, kind of like the sun. We orbit around the sun. Then you've got the charges. The charges would be negative for electron, proton would be positive, and for neutron, there's nothing. Same thing for the symbol. All right, so then we're going to go over to AMU. And what AMU is atomic mass unit. Okay? So you got atomic mass unit, and what you see with atomic mass unit is a number that's kind of hard to memorize. Just don't. It doesn't matter, okay? But what you do need to know is atomic mass number. Atomic mass unit, not so much. Atomic mass number, you do. The atomic mass number, I know the definition of what atomic mass unit is, and that's the actual mass of the subatomic particle. But the atomic mass number is the rounded off version of it, okay? So if you look at the AMU, the proton and the neutron are very similar in size. The neutron is a little bit bigger than the proton. Again, we'll talk about that. And then the atomic number is going to be atomic mass number is going to be 1, right? Round it off. So you got in the proton is 1.00728. You wouldn't round that up to 2. You'd round it down to 1, right? So what we got then is that 2 things that we can get from that. One is that I've misdrawn the size of the electron. The electron then would be tiny. All right? So the electron is little bitty in comparison to the proton and the neutron, and even the proton and the neutron are tiny. Ever seen an atom? And looking at your hand, you know, you got a handful of atoms. Can you pick them out individually? No. So there was a guy, his name was Richard Feynman, and he was a lecturer, I think at Caltech, physicist, brilliant guy. Probably, you know, he was, I guess you could kind of say the next Einstein, right? So Einstein came and went, and you know, of course Tesla, but he was right up there, brilliant. And you can still find his lectures on YouTube. And he did one on the atomic structure and you know how we kind of developed the understanding that we developed of atoms. He said if you took a tablespoon of water or a slide, a microscope slide with just water in it, and you magnified it up 1,000 times. So it's just a little tiny amount of water and you magnified it up 1,000 times. What it would look like is that maybe this entire room was, you know, the floor was water, okay? You magnet up another 1,000 times, what is this room, maybe 50 by 50? Something like that. So it'd be 5,000 feet by 5,000 feet. It's a lot of room, right? So now you've got a lake area, as my math is probably wrong on that, but you have a lake area that might stretch from, let's say, here to the loop, if we go east, maybe to the loop if we go south, right? So it's a big area. But still, you look down on it, it's just water. Doesn't look any different. But the magic happens when you magnify that up maybe another 500 to 1,000 times. Okay, now you've got an area that stretches from about here to Chicago. You know, this tiny speck of water is now so big that it looks like an inland sea that takes up the entire center of the country. But it still looks like water if you look down on it. But if you get down on the level and you look across it, it's not flat anymore. What it is it's bumpy, like that. Okay, so it's got individual pieces to it. It's perfectly still as we understand water. You know, you don't have any waves going or anything like that. If you look down on it, it looks like it's perfectly still. But if you look across it, it looks like it's still and flat if you're looking down on it. But when you look across it, you notice 2 things. One, it's not still. And 2, it's not flat. It's bumpy, and each one of those bumps are just kind of buzzing around, bumping up and down, okay? So individual water molecules, and they're in motion. So what we can deduce from that is that with the individual water molecules, we've got 2 things. We've got individual pieces that are completely separate from other pieces. That's number 1. And number 2, something is moving around, right? So you got these electrons buzzing around the outside in constant motion, really fast, around the outside of the nucleus of the atom. So that's water, but we can apply the same thing to the atom. The water is made up of hydrogen, oxygen, which are individual elements, and those elements we call atoms, right. Right, so that's where we are now, and we identify the subatomic particles as what we did, but what we've got here is subatomic particles that are so small you can't see them, right? Can't see atom. I should magnify it up a whole lot, right? Can't see atom, individual atom. And then if we start talking about electrons, okay, so these are too small to see. They're so small that you can't see them. And these are so small that they, what's the atomic number of an electron? Zero. So, so they're so small they almost don't exist, right? So that's the things that we're talking about. And in the comparison that we're making, this is the sun and these are the planets. How big are we compared to the sun? Tiny. Tiny, right? And the sun compared to most other stars is likewise tiny. It's very, very small. So again, looking at our atomic structure and comparing it to a solar system, our solar system, other solar systems, then what we can again deduce is that there are different solar systems that are different sizes, potentially. The nucleus can be much larger than our nucleus, right? Our sun. So that's what we've got, is that inside the nucleus of the atom, we can have all kinds of protons. We can have 2 protons and no neutrons. We can have 2 protons, 2 neutrons. We could have a bigger one that has 10 of each, right? So we've got a bigger sun. So what do we know about planets and their size and how we would relate to them? We talked about this chapter 1, I think it was, when we talked about space camp. What happens if you go to the moon?
Gravity, gravitational pull.
Gravitational pull is much lower. You might be able to knock somebody off the moon, right? It's much lower than what it is on Earth. What's the difference between Earth and the moon?
6. It's a difference of 6.
Yeah, the gravitational pull is 6 times, but size-wise, which one's bigger? Earth. Earth, right? So what do we say about Jupiter?
It's got more.
It's bigger. Granted, it's a gaseous planet, but it's bigger. We said it's vacuum cleaner of the Earth, or vacuum cleaner of the solar system. And why is that?
Yeah, it's
Gravitational pull.
Gravitational pull is greater. So what we're going to find is that because the mass of the atom is found inside of the nucleus with protons and the neutrons, that's where our it's mass, but we're going to say weight of the atom comes from, because there is a correlation here. And I touched on that the other day, the difference between aluminum and lead. Same quantity that you have in your hand, size-wise, the lead's going to be a whole lot heavier, right? So with that in mind, the weight's going to come from the nucleus of the atom. If we have a bigger nucleus, we're going to have more weight to it. If we have more weight to it, then we're going to have a greater gravitational pull. Okay? So, if we have an atom, let's say that's just got 2 of each, then we're going to have a specific gravity between the electron and the nucleus of the atom. So you're going to have a pull. Let's actually do this. You're going to have a specific pull between that electron and the nucleus. Okay, so you're going to eliminate that. So it's going to be a specific pull. It's just, think of it as gravitational pull, but what we're going to call it is a binding energy. Okay, so we've got a binding energy between the electron and the nucleus, and that binding energy, again, is analogous to gravitational pull. It's what holds the electron into its orbit. Gravitational pull of the sun is what keeps us into orbit. If it didn't have a gravity, where would we go? Outer space. Then we have a big problem, right? Smacking into stuff, and we wouldn't have the heat from the sun, all that, right? So gravitational pull keeps, or binding energy keeps the electron in its orbit around the nucleus of the atom. If we make that nucleus bigger, we're going to go with 10 and 10 again. Now understand that this 10 down here, I'm just putting that in just to add neutrons so the protons aren't lonely. Then what's going to happen to that gravitational pull? Now, instead of being orbiting around our sun, we're going around a bigger star. If we're at the same distance, what's gonna happen to us? Two things, really. One, it's gonna burn us up, and two, it's gonna suck us in, right? We've got a greater gravitational pull on our planet, and it's gonna pull us towards the star until eventually we fall into it. All right? So the gravitational pull gets higher with the bigger neutron, or bigger nucleus, rather. Gravitational pull gets higher, so we've got a greater binding energy. Okay? So we've got a couple of forces that keep us, in our orbit, and it's not just the binding energy. The binding energy is kind of analogous to what we call centripetal force. Okay, you're more familiar probably and use the word centrifugal force. We're going to use that too. Okay, so we have to have two forces working together that offset each other, kind of like the positive and negative charges in protons and the neutrons, or protons and the electrons. We have centripetal force, which is basically, I'm just going to put it there, just say centripetal force. Okay, centripetal force is basically the gravitational pull of binding energy of the electron to the nucleus of the atom. But at the same time, we have to have enough speed going in order to keep it from falling into the nucleus. Okay, so if we had a bigger star, we'd still have a problem with, and we were at the same distance that we are from our sun, we'd still have the same problem with burning up. But how could we keep our planet from falling into the sun? We couldn't, but what would have to happen in order to keep it from falling into the sun?
Greater distance.
What's that?
Distance.
Yeah, well, that would be one solution, but what if you couldn't increase the distance? It's got to go faster, right? So we can, again, look at our solar system and kind of make a comparison. Mercury orbits the sun a lot closer than we are, and it also orbits the sun a whole lot faster than we do. Okay, and you got Mars, and it's going a little bit faster than the Earth, and you've got the Earth, and so on and so forth, right? So we have a tendency to see our orbit as being very circular, and it's not. It's kind of elliptical. Elliptical is kind of like an oval. And the further out we get away from the sun, the more oval it becomes. Why is that? Because distance. The further you get away from the sun or the nucleus of the atom, the less that gravitational pull becomes, right? So what's the very last planet?
Well, it's not Pluto.
Wait a week, it might be Pluto again. What is it?
Neptune.
Neptune. Right? Pluto used to be.
Yeah.
And they jerked status away from it. They gave it back, jerked it away again. Right? But let's assume Pluto is still a planet. Is it always the last planet?
Planet X.
Ah, okay. We're not going to get into that theory. But the answer is no. That when those planets, we get to those outer planets, those two outer planets, their orbit is so elliptical that sometimes one is closer and sometimes the other is closer. Okay, so they're greatly ovaled. So, you've got overlapping, orbits like that. So sometimes Pluto's closer, sometimes it's not. So what would make them be less elliptical and more rounded? If they had a greater gravitational pull. Comets. Anybody seen a comet? Has there been? Okay, yeah, I'm getting a couple of head nods. So why don't we see comets all the time?
Jupiter's Bohr.
That's one of them. All right, so did I mention this before the shoot? Well, yeah, we talked about the comet smacked into Jupiter, Shoemaker-Levy, I think it was. Or was it? Yeah. I didn't post that video. I'll try to remember to post it. But that's one, yes. But the other is that it doesn't, okay, it's traveling so fast that it passes the sun by and it gets close enough to us that we can see it. But it's going so fast that the sun can't lock it into a specified orbit. Does that kind of make sense? So these things are going way outside of the solar system. And they kind of slingshot around and they go back out. One very famous, predictable comet was Halley's Comet, is Halley's Comet. It comes through like every 78 years, something like that. Right? Well, where does it go? Just go home and make a sandwich, sit on the couch and watch TV? It's way out past the solar system, but it's still got the gravitational pull so that it's going to come back. It's kind of like Old Faithful. It's going to come back, and it's going to be a predictable, I don't know when the next time, I'm going to be gone. Y'all might be still here, but I'm going to be gone by that point. I think the last time it came through, I think I was close to y'all's age, so, you know, you'll probably see it. You might need glasses, but you're probably going to see it in your lifetime. All right? So, what do we learn from all this? Well, a number of things. One is that the closer the planet is to the sun, the greater the gravitational pull. Right? The greater both the centrifugal force, centrifugal force and the centripetal force to lock it into its orbit tightly. The bigger the nucleus, the bigger the sun that we're orbiting around, the same thing happens. Okay? So why does all this matter? For a couple of different reasons. One is, let's go back to our small nucleus. So we've got protons, we've got one proton, we've got one electron, we've got one proton, we're not even going to put a neutron in there. We've got one proton, we don't have all of these other orbits. We've got one electron, one tiny little lonely electron. What element do we have? Hydrogen. We've got hydrogen, right. So if we only have one proton, in a word, how big is our nucleus? Small. So in a word, what is our gravitational pull? Small, low, right. So let's say that hydrogen is not a gas, but it's a solid, right? If we made our anode out of hydrogen, let's say it's metal instead of gas, what would the binding energy of that electron be? Just in a word, very low, very low. Well, the two ways we create X-rays. Brims and characteristic, right? So what is brims? What? Yeah, it means breaking, but what is it? What is it? What does it depend on? Gravitational pull, right? So what's the gravitational pull of one proton? Again, in a word, not very good. So we send an electron coming into our target, and it's going really, really fast. What's the effect of that one proton going to be on that one electron? Minimal. So what kind of brims X-rays can we create if the brims creation is dependent on the loss of energy caused by the gravitational pull of that nucleus? Nothing. It's just gonna pass on by. We're not gonna have anything, essentially. Okay, so what about characteristic? We knock this thing out. It's held in by how much force? Not much, not much. So we knock it out. We create an X-ray photon because it's got to be replaced. It's got to be replaced. We're going to create an X-ray photon, but what's the energy of that X-ray photon? Useless, right? So how can we affect a change in both of those? whole bunch of protons, whole bunch of protons, whole bunch of neutrons, right? So then we've got a whole bunch of, if our atom wants to be neutral, we've got a whole bunch of protons. What are all those charges? Positive, so we're going to have a whole bunch of electrons as well. I'm going to draw this very simplistically. This is not how this is going to turn out, but we're going to have a whole bunch of electrons as well. Okay, so a couple of things there. My electrons now need to come, projectile electrons now need to come a little bit further out because our nucleus is way up here. So our electron comes through. What's the likelihood that that nucleus is going to grab that electron and change its trajectory? Better or worse than before?
Better.
Much better, right. So is it going to lose more or less energy as it goes? It's going to lose more energy, which is going to give us a higher energy X-ray photon. So that's number one. So we were looking at something. The overall atom, again, is so small that we can't see it. And we're shooting for electrons that are so small that they almost don't exist. Well, we'll make it a bigger one. So what's the likelihood of us hitting one of those electrons if I have more of them? Much higher, right? So for illustration, if I only had one student sitting in the room and I turned my back and I picked up all these dry erase markers and threw them over my shoulder, what are the chances I'm going to hit that one student with one of those dry erase markers?
Not great.
Could have happened, but it's not great. Yeah. I got a room full of you. How many am I going to hit?
You're hitting someone.
I'm hitting somebody. Right. Somebody's getting hit. So kind of the same thing as far as characteristic goes, right? As far as BREMS goes, it doesn't really have an application in that example. But anyway. Okay. So what's the takeaway from this? Positive charges in the nucleus, neutral charges in the nucleus, negative charges outside of the nucleus. So what we have a tendency to think of when we think of our atomic structure is, well, first, before I say that, I mix these up, is we've got electron shells, orbits with, shut up. I almost did it again.
Oh my God.
All right, here we go. Incoming. All right, go away. All right, where was I? Oh yeah. We have a nucleus, right? This is just falling apart. And we have one proton. To make our atom neutral, electrically neutral, how many electrons do I need to have? One. So we got, shut up! We need one electron. It's neutral. You're going to have a tendency to say this is stable, okay? And it might be. It is more stable than this, right? But stability, we're going to talk about next week. That has really to do with the weight of the nucleus of the atom. We're going to talk about that next week. Okay, so this is electrically neutral. It is more stable. It's what the atom wants. But do we have ions that we? You still giggle. All right, duck. Do we have ions? Sodium chloride, right? So, can we have ions? Yeah, we can have ions. Doesn't necessarily mean that they're unstable. It's just not their preferred state, right? So we've should have the same number of protons as we do electrons. So what if I add a proton? What should I do? Add an electron, right? So if I add another one, now what?
Add another electron.
Add another electron. Am I going to put it right here? No. That's what you might think, but what we're gonna have are a prescribed number of electrons capable of being in a shell, okay? So the innermost shell can only have two. And how we're gonna name these shells is they're alphabetical, and for some reason, probably some guy who couldn't put the right lid on a dry erase marker came up with this idea, called that the K shell, and then it's alphabetical after that. So the next one would be the L shell, and it can have more electrons in it than the K shell. So our L shell is gonna have one, our K shell is gonna have two. Okay? Now, a few things about the shells, all right? The things that I want you to think of is this, all right? So we got a bigger sun in our solar system. What's gonna be the gravitational pull compared to a smaller one?
Higher.
It's gonna be higher, right? So what would, if I took this thing and I made a bigger nucleus on it, then would it not, now we've got, maybe 9, okay? Would it not make sense that the gravitational pull would cause these electrons potentially not to fall into it, but they might speed up and they might get closer? Potentially? Yeah? Okay. So I've got 9 here, so I've got 2 there. How many would I naturally have in my L shell? 7. I might have 7, right? Maybe. So what you'll find also, though, is your shells don't necessarily have to fill up before moving on to the next shell, okay? What I mean by that is if you look, well, just look on page 39, just the page over. So you're looking at uranium, and how many shells are in the outermost shell? 2, right. Now if you flip over to page, let's see, that would be 1, 2, 3, 4, 5, 6, 7. So that's 7th shell, so that's a Q shell. How many electrons can be in the P shell? If you flip over to page 40.
72.
Yeah, you can have 72. So you look back over at page 39, and how many is in the P shell, the second furthest out shell? Is that 72?
No.
Not even close, right? So you don't necessarily have to fill up every shell before you move on, okay? I'm not going to ask you to calculate or memorize how many electrons are in each shell, but you do need to know 2 things about electron arrangement. One is that you can calculate how many shells or how many electrons a shell can hold with a formula. It's a simple formula, really. It is 2n squared, okay? So it looks kind of complicated, but it's not, okay? The n stands for the number of shell we're talking about. So the innermost shell is a K shell, okay? So just kind of put away the alphabet for now and say this is the first shell, okay? So 2 times 1 squared is what we're looking at. So according to order of operations, what's the first thing you do? Exponents, right? So what does the square mean? It's times itself, right? So that would be 2 times 1 times 1. 1 times 1 is 1. 2 times 1 is 2. So the maximum number we can have here is going to be 2. 2, right? So let's do it again for the second shell. Okay, so 2n squared is 2 times 2 squared. So now we've got 2 times 2 times 2. That would be 2 times 4, and that would give us how many? 8, right? Okay, so if I asked you, okay, M shell, how would you set it up? 2 times 3 squared, so it'd be 2 times 9, so it would be 18. Okay? So that's one thing, is that you can determine how many can theoretically fit inside of a shell using that formula. That's a maximum you can put in each shell. Now, does each shell have to get to that before moving on to the next one? Well, we just saw that with uranium. No, is the answer. And as a matter of fact, you're going to find that in some cases, you don't want to fill them up. I got it right. You don't want to fill them up. Yeah, I'm childish. You don't want to fill them up sometimes. Okay, so the most stable an atom will be is if they have 8 in their outer shell. Okay, so that's the second thing you need to know. First thing is, how many can it hold? Can it theoretically hold? 2n squared, right? How many does it want? 8, right. So, water stable?
Water,
Yeah, water very stable. Water very, very stable. What's it made out of? Two hydrogen, one oxygen. So let's flip over to page 37. You've got the elemental table. The elemental table was first described by Mendeleev, and I forget exactly how it's in here somewhere, but anyway, he identified something like 50 different elements, and now we've got a whole lot more than that. A lot of those are man-made elements, are highly unstable, and we'll talk about that again next week. But we've got 92, it's 118 known elements, 92 natural and 26 man-made. But where is oxygen on that? Number 8, right. So what we've got in that 8, what that 8 is just the number of protons. That's all it means. The number of protons, number of positive charges determines what the element is. Okay, so if you have 8 protons, how many electrons should you have? 8, right. So I'm going to get rid of this. I'm going to go back to really bad drawings. So you've got oxygen. So how many electrons can you have in the innermost shell? Always 2, right. And then you've got so that's K shell, that's L shell. So you've got 8 protons, who knows number of neutrons. Doesn't matter at this point, but you've got 6 buzzing around out here. Okay, how many does it want to have? 8. Can it have 8? It can. What do you have if you've got 8? An ion, right. You got too many negative charges, you got an ion. If you have too few negative charges, you have a ion. Okay, so ionization is all about the number of electrons. Did I put the right? I put one too many, didn't I? 1, 2, 3, 4, 5, 6, 7. Okay. Well, I'm going to leave it. I'm actually going to leave it. I'm going to add another one. All right. So, how many electrons do I have in my outermost shell? Now,
8.
I've got 8. Right. Is your atom going to stay that way though? No, it's going to shuck those. You become ionized in the wintertime. Did you realize that? In wintertime, you don't do it in the summertime, but you become ionized in the wintertime. How do I know that? Pow! Exactly. Exactly. Yep. You scoop up electrons as you're just moving through the atmosphere, rubbing across carpet, seat in your car. I'm going to show you a video. I think it's also in Canvas. And if it's not, I'll put it in Canvas. But anyway, you scoop up electrons, you become ionized. You got too many electrons for the number of protons you have in your body. So you got to get rid of them. And the way you get rid of them is static discharge. We're going to talk about that once we get into electrostatics and electrodynamics. So we can have 8, but it's going to shuck those, right? But, and this is getting into next week as well, what if that electron was actually attached to a different atom? And let's say that electron was also attached to a different atom. What atom only has one electron? Hydrogen. What about just your own? Water. Water. Right, so how many electrons do you want in your outer shell? Does an atom want in its outer shell? So is oxygen happy with that? Is hydrogen happy with that? Yeah, all three of them now have 8 in their outermost shell. They're just sharing. This is what we refer to as covalent bonding. We're going to talk about that more next week again. We're going to talk about 2 different types of bonding, how we get to each one, but this is a shortcut to it. They're sharing electrons for the sole purpose of getting 8 in their outer shell, covalent bonding. Very hard bond to create, very hard bond to break apart as well, compared to ionic bonding. Ionic bonding, you're just smacking around electrons, right? Okay, so the takeaway again from that, 2 things to remember about well, more than that, but as far as the arrangement of electrons, 2 things to remember. How many can each shell have? 2n squared. Just work it out. All right. So how many do you want in your outermost shell?
8.
How many is the maximum you can have in the outer shell?
8.
2n squared.
2n squared, but they're going to stop at 8. Yeah. So kind of a little of both, really. But theoretically, the maximum you can have in any shell is going to be 2n squared. Okay. I see what I've missed because I have been all over my notes here. Mass of the atoms in the nucleus, the area is mainly empty. Don't confuse those 2. The mass, the bulk is going to be in the nucleus. The area is empty, right? Atomic mass unit is the actual mass of the particle. Individual particles. Atomic mass number is a rounded equivalent. The atomic number, and we'll talk about this again next week as well, is just number of positive charges. That identifies the element. The neutron just gives weight, size to the nucleus. Okay, we'll talk more about the neutron in decay. Nuclear decay on Friday of next week. So atomic number, just number of protons, determines the element. Change the number of protons, what do you change? The element. Yeah. Change the number of neutrons, what do you change? Not the element, right? Change the number of electrons, what do you change? The charge. Right. So again, when we're talking about ionization, we're always going to be talking about the electron, right. So atomic mass is protons plus the neutrons. So again, the electrons get left out of the discussion. So it gives us the mass of the element. The electron binding energy increases. Okay. So electron binding energy increases the closer to the nucleus, bigger sun, closer to it, greater the gravitational pull, right? So 2 things to remember about electron binding energy is higher, closer to the nucleus, and it's greater in atoms with a large nucleus. More protons, more neutrons, then the greater that gravitational pull. Again, we're going to expand on that on Friday of next week. Electron arrangement, 1s8, 2n squared is maximum centripetal force. We talked about that. Centripetal force is basically the gravitational pull. Centrifugal force is the speed with which they're going around the nucleus. Got to have them both. Loose centrifugal force, it falls into the nucleus. Loose centripetal force, and your electrons fly out into no man's land. What's our time?
10:03.
10:03.
So you